Okay, that's why 我们那个标准就是
你们要 intro 啊，就我这一辆。
是个小 intro，那都理解。哦。
健美老师就是一个 design， 请问没有空啊？好像物理系的比那个数学系还要多的感觉。
Because everything six friends. And to change politics into business. Like, are you not within this year's? Clear.
都这样。少了好多人。Too much people today. 被劝退。We'll be starting our seminar in a few minutes. We'll wait for a while. Let's see if there's a. Yeah, we'll start at 7:35. Yeah, 我给你就出来。哇，记忆真好。进来就Nice to meet you. 因为是给我下个礼拜介绍过的。抛在里面的不要在里面，或是多少分了？
这其他新谈的，然后还在这里。很多他们两个，他们东西是在那边的。
Welcome everyone to our second week seminar, and we'll be starting right now. And I'll pass the mic to our speaker today, Ryan.
Okay, so I think most, if not all of you have already seen me before, so I don't need to intro myself. Okay, so when I was saying time, we pick up where we left off last week. So last week we basically stopped at the statement of Hilbert's Null-Sentence stars, which says that we have a one-to-one inclusion reversing correspondence between affine subsets, affine algebraic sets in affine n space an, and radical ideals in the ring of polynomials in n variables, right? So in one direction is given by taking the zero set, and the other direction is by taking the ideal. So we have two functors here. Okay, so I should just to add a bit of because we don't see an in because now Sentence stars is obviously not an English word, right? So because we are a bit rushed last week, so I forgot to say. It's just to mention. So the word now Sentence stars is obviously German. So you break it down into three parts: now, stellen, and starts. So now everyone knows now means zero, and then stellen means place or set, having, and then such is statement or sentence. So usually if you Google a translation online of the word now sentence, usually they'll tell you something like zero. Wikipedia says zero locus theorem or zero set theorem. That's the English translation that you can take. Okay, so which is obvious, name is obvious, right? Because we're talking about how zero sets correspond to radical ideals, right? So that is just a bit of German language stuff. And then last week we ended with an example that the example we did last week, -1, is an algebraic set, and it corresponds to the radical ideal, which is the principal ideal generated by x squared minus 1. And we treat it as a homework, right? That should show that it's indeed a radical ideal. So it's a demo of Hilbert's Null-Sentence stars. And so now we'll do a few more examples and we'll generate a few more examples using Hilbert Null-Sentence stars instead. Last week's example was we are verifying Hilbert's Null-Sentence stars. Okay, so it's a bit of a different thing. And before going to the more interesting examples, I just want to warn you about the framework of our theory is that, remember, we always assume that our field is algebraically closed because now I want to tell you, last week I didn't manage to tell you what would go wrong. So now I'll tell you what would go wrong if we do algebraic geometry over a field that is not algebraically closed. For example, real numbers, our favorite R. So our most familiar R. So we consider, let's take our base field to be real numbers. So we still can define affine space over real numbers, all those things, no issue, but it breaks, but this one-to-one correspondence would break down in this way. So our favorite non-example of a polynomial over real numbers is x squared plus 1, right? Our favorite irreducible polynomial that's not a zero polynomial and it has no roots. So in this case, so we're in affine one space over R. So we're basically on the real line now. So the zero set of x squared plus 1 is the empty set, right? Because x squared plus 1, everyone knows, has no real roots, right? So the zero set is empty. And then what is the ideal corresponding to the empty set? So we have the ideal of VF is because of the okay, no need that. So VF is the empty set. So what's the idea of the empty set? Meaning, what is the set of all polynomials over real numbers that have no real roots, no common roots? Take everything, as usual, take everything, right? So all polynomials. So, and we have polynomials over one variable, so Rx, right? So the whole ring, right? So the inclusion reversing property still appears to hold for now, but now we've gone from one way and one way, but we haven't really checked the cycle, right? So the problem here, so what's the problem here? So the problem here is that when you do that, we want to start with the idea. Okay, so we started with the polynomial f here, right? Yeah, so basically, in other words, you can rewrite VF as V of the principal ideal generated by F, right? That's one way to say it. So that's the ideal we started off from one side. Then we translated over to the affine space side, get the empty set. Then we take I back, and we got the whole ring, not this ideal. You see the problem here? So now the problem is put in a bit more elementary, or if you're smart enough, maybe you will think even like a stupid way to say it is that if we have a bijective correspondence, because now what our issue is, the whole ring is clearly radical, right? The whole ring is a radical ideal of itself. No issues, right? And then the ideal generated by x squared minus 1 is also radical because it's irreducible. But are these two ideals equal? Not equal. So not equal means what? Means we have found that the empty set corresponds to two different radical ideals. So we lose the bijectiveness. Okay. So in this case, actually, there's no issue with inclusion reversing. There's even no issue with relating an algebraic set and a radical ideal, because these two are both radical ideals. So no issue with that. The issue is with bijectiveness. It's no longer one-to-one now. So meaning that if we do algebraic geometry over a non-algebraic closed field, got to be careful, right? Okay, so that's one thing that we want to emphasize here. Then next we'll generate a few more examples with which the future speakers will go into more detail. So actually my job today is kind of today's syllabus is kind of like I'm like laying a bit some foundations for the next few weeks to pick up in more detail. So the interesting parts are actually next week onwards. So the first 2 weeks is just me going through all the dry stuff, and I hopefully make it not feel so dry and not feel so abstract for you. I hope I can achieve this in these 2 weeks. Then we'll move on to the more interesting, more geometry things next week. Okay, so these 2 weeks is really preparing all the language to do the geometry. Okay, so last week we did A1, right? So wait. Okay, we have more examples? No, we do the examples after introducing what it means to be irreducible, or after we define, after we define what a variety is. So before you come to this course, this seminar, you've probably heard of that when you already heard that the idea that basically the objects that algebraic geometry is concerned about are mainly so-called algebraic varieties. That's probably what you heard before. So we'll define that in very quickly, maybe in half an hour or 1 hour. So, okay. So now, second thing to recall from last week is I want to draw some properties of zero sets. So again, first thing to recap from last week was the Naus-Allen-Stokes. And then second thing to recall is some key properties. How to spell property? Keys. Okay. Of VS. Right. Okay, so the first thing we noticed last week was that empty set is algebraic, right? And the whole space is also algebraic, right? Okay, we got it. So empty set is the zero set of all polynomials, right? And then the whole affine space is the zeros of the zero polynomial. You got it? So in other words, empty set and the whole affine space algebraic. And then we call it what? Finite unions of algebraic sets are algebraic. I probably didn't write this statement last week, but the statement you'll recall is the statement that what is the zero set? What is the zero set of a union of algebraic sets? Of a union of polynomial sets? It is the no, I should write the other way around, sorry. I should write it as what is the union of VSIs? Recall that? It's the V of something, right? So it's the V of their products, right? That's the version we did last week. So translate another way means union of algebraic sets is an algebraic set. Okay? So, and we have a synonym for property, remember? So we have arbitrary intersections of algebraic sets is algebraic. So the statement was, what was the intersection? And then now we're not in a finite union. Now we're arbitrary union, so we can have any kind of index, right? So we index S by alpha. So intersection of zero sets, what was that? Remember that? It's the zero set of something, right? The zero set of the unions, right? So that was what we recall last week. So those of you who know general topology, you see familiar things, right? I rewrite in a different way. So remember the axioms of topology? The empty set and the whole space must be open. In this case, we want it to be closed. And indeed, they're both open and closed. And then you have arbitrary unions of open sets must be open. So when you take complement, we get finite unions. We take complement, you get arbitrary intersection. You should say that the other way around. So you have arbitrary intersection of closed sets. It's closed. And then similarly, we have finite intersection of open sets. It's open. So translate to closed will be finite union of closed sets is closed. Right? So you see an identical structure here. So now you can use the language of topology to say that. So this means that the affine algebraic sets form a topology on AN. And this topology is called, now you know the name, Zariski topology on affine N space. So it's meaning meaning that we define the Zariski topology to be, we define the closed sets of this topology to be the algebraic sets. So that's the trick that Zariski exploited to give it a topological structure. Okay. So I should complete the sentence, say by defining the closed sets to be exactly the algebraic sets. So you see the structure here, or about Zariski topology. So actually, if this is the course that I designed myself, or what, I'll just present this thing in week 1 actually. So I delayed it a bit to just to follow the theme, the titles that we set up every week. But turns out not so bad. We're not losing anything at all. Okay, so we're just drawing the key properties and say, actually these are the properties of a topology. So actually we found a topology for AN. Okay. Okay, so the next concept is that I want to tell you what is an irreducible space. What is an irreducible space? Okay, so now we're talking. So now you see, like from this point onwards, we're actually talking about AN as a topological space, right? Because we have put a topology on it already. Okay. So okay, now I want to define a topological space X is said to be the same word, Noetherian, a Noetherian topological space. Means that, how should I write it? So, no, I'm not talking about Noetherian yet. I want to talk about irreducible first. So what's an irreducible space? So in linear algebra, do you hear the term of irreducible subspace? What's an irreducible vector space? It's a similar idea. So an irreducible vector space in linear algebra is a vector space where you cannot split into the direct sum of two smaller subspaces. Right? So it's the same thing here. So a topological space is irreducible if it is not the union of two proper closed subspace. And in this case, because we put Zariski topology on AN, so in this case, we're actually looking at the Zariski topology, not any other topology on AN. The other topologies on AN, for example, those that you're familiar with, the metric topology, the Euclidean topology with the Euclidean distance, all those things, Euclidean norm. So we're not in that topology in algebraic geometry, okay? So So we say a space is irreducible if it's not the union of two proper closed subspaces. Yeah. Close under the what? What? Are you talking about projective limits? Not that one, right? Oh, you mean you want to relate the Zariski topology and the standard topology? Is it? I haven't learned anything. I didn't learn anything about that myself, actually. I haven't thought of this question, actually. Yeah. Yeah, so maybe you can remark a bit. So, yeah. So, yeah.
And any metric you define will give you different open sets from those here. I think this case the operator will consider as C. So if it is C, then we do everything in the CN. CN is the standard topology, which is the yes. So you have metric both. Yeah, you have the standard metric topology of CN, but it's very different from from Zariski topology. Zariski topology has way fewer closed sets. Yeah.
No, I think my point is to see why they're.
Yeah, so if something is closed in Zariski topology, then it is closed in the Hugo set, but not the other way around. So maybe, yeah, fine. Not sure.
Yeah. Yeah, so the short answer to that question is that the Zariski topology is a rather coarse topology.
Yeah, that's true. Yes. Yeah, that's what I was. Yeah, that's what I wanted. Yes. I mean, Zariski often have less confidence.
Yeah. So generally, the Zariski topology. Hey, there's another interesting fact about Zariski topology is that it's almost never Hausdorff. Have you heard of a Hausdorff space? Anyone? So a Hausdorff space is a topological space where you can split any 2 points by disjoint open sets. So for example, our favorite R, C, they are Hausdorff. Okay, because any 2 points, you can always find a ball small enough that don't intersect each other. That's an intuition of a Hausdorff space. So in the Zariski topology is almost never Hausdorff. In fact, there's a theorem saying that if you have a Hausdorff space in the Zariski topology, it has to be finite. Did I recall that theorem correctly? It's in Milne. But we're skipping details about topology here. So okay, just a remark. So Zariski topology is much coarser. That's the short answer.
Almost.
It's almost. I mean, the Zariski topology is almost never a Hausdorff topology. That's what we're saying here. Yeah. So so we'll mention as an example that even A1 is not Hausdorff. Basically. Yeah, because last week we did that the algebraic sets in A1 are either empty set, whole space, or finite sets. Remember that? That's the example of A1 we did last week. Where was it? Yeah. Remember this example? That's true. So even A1 is not Hausdorff actually. Yeah, it has to be finite. That's all. So there's a theorem in Milne. Yeah. Yeah. Yeah, that's actually I think what you mentioned is from the way I read is it was more, I think I read that statement in the concept of Noetherian space. All Noetherian spaces have that concept that any two open sets must intersect. Yeah, that's irreducible. Yeah. 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 So now we have to. That's why I wanted to introduce the term irreducible immediately first before more discussion. Because we want more to build up more vocab. Okay, so next vocab that we say is concept of irreducibility. So the other way, so meaning irreducible means you cannot break this space down into union of two smaller closed space. Okay, doesn't need to be disjoint. Okay, so this is the intuitive way, the English way to write the definition. So what's the math way to write the definition? The math way is that if X is the union of, for example, X1 and X2, where X1, X2 are closed subspaces, are closed proper subspaces of X, then we say we cannot break down into two smaller pieces, right? That's what we're saying. So now we assume we can break into two smaller pieces. So what does it mean? If it can break, it means either one piece must be the whole thing, right? That's what it means to be reducible, right? So then it means that then either X is X1. Maybe I should write it that. Maybe either X1 is the whole space or X2 is the whole space. Right? So that's the definition of irreducible. So just think of it intuitively. It means you cannot break down into two smaller closed subspaces. That's all. So the keyword here being closed. And the topology we mainly care about is Zariski topology. Okay. Okay, so what's next now? Because we ordered a lot of things, so things get a bit confusing here. Irreducible. Yeah, okay. Now and okay, so I mentioned a few equivalent definitions. So an equivalent definition is that yeah, we just mentioned one of them just like a few minutes ago, meaning that any two open sets in X have non-empty intersection. So here open sets, those of you who don't know topology, just think of open sets as complement of the algebraic sets. So for example, -1, 1 was for example, just now -1, 1 from last week. This is an algebraic set in C, right? In A1C, right? So an example of an open set is all complex minus throw away that 2 points. That's one example of a Zariski open set in A1. Okay. So I'll just state here without proof, and I'm not even sure if we're going to apply it today, but Yeah, which one? Okay. Any two? Oh yeah. See? Yeah. Yeah. You're correct. I don't need the word proper there. Yeah, I don't need the word proper there. Yeah. Yeah, that means if we break down into closed subspaces, it can be only one component. Okay. Okay, and another equivalent definition is that any non-empty open subset of X is dense in X. Those of you who did MA1 heard of the word that what's a dense set, right? In the metric sense. But the definition, the more general definition we'll use here is that of what a dense set is, that is meaning that is the closure of that set in the whole space is the whole space. Okay. So these are the equivalent definitions of irreducibility. And I think is Larry here today? Yeah. So I'm not sure if you'll use some of these results next week, right? To show that the dimension of an Fi of AN is equal to N, right? Not sure about that. I remember you need to use some concepts like irreducible and Noetherian. Yeah. Yeah. Yeah, because you just define using that the shader. Yeah, we'll do the Noetherian later. So today, part of today is also to help Larry with some preliminaries so he can use it next week to do interesting stuff. Unlike me, who is in charge of the dry stuff. Okay. Okay. So just one more property I want to state about irreducibility is that one big observation here is that wait. This what is this? Is this? I get confused of which section this thing is in. So okay, that's not this section. Damn it. Okay, so now we continue with more vocab. So now I can tell you what an affine variety is. An affine variety is an irreducible affine algebraic set. That's all. Then of course the sense of irreducible is in the Zariski topology. Okay. So now this is the classical way that people use to define affine varieties. So there's a more modern way to define a general variety, which is uses modern language of you need to know what a pre-variety is, and you need to know what a pre-variety is, you need to know what a scheme is. When you need to know what a scheme is, you need to know what a sheaf is. So leave that for the modern course. Okay, so we take the more classical definition here. So when you think of a affine variety, just think of it as an irreducible algebraic set. That's all. Okay. Okay, so we start with a few examples. So I prefer to do the general theory first. So maybe I'm going to state this result first. So it's an extension of the Hilbert-Null-Sallenstart. So remember Hilbert-Null-Sallenstart, we say that if we have this correspondence between algebraic sets and radical ideals, right? So now we're talking about a special kind of algebraic set, mainly irreducible sets, right? So now the question is, what does an irreducible algebraic set, what kind of ideal does an irreducible algebraic set correspond to? So turns out that if A is an affine algebraic set, A and K is an irreducible algebraic set if and only if IA is a prime ideal. So clearly prime ideals are radical. If not, this thing would not make sense. So okay, so now we can break down the picture of Hilbert-Null-Sallenstart a bit more. So let's copy it. So let's copy this. Let me copy this first. So in other words, now we have a breakdown of this correspondence. So we have irreducible affine algebraic subsets of AN corresponding to prime ideals in the polynomial ring. Okay, so, and then later we'll show another special case. I think it's called the weak Null-Sallenstart. So is that what kind of algebraic set corresponds to maximal ideals in the polynomial ring? That we'll answer that very soon as well. So I think, of course, we hope to focus more on the concepts, more on the ideas. So I think I'll skip the proof on this one. I originally thought of presenting the proof, but due to time constraint, I guess better not first, unless we have time at the end. It's not difficult, and I find it enlightening, so it's quite interesting. So maybe now I have to remind you what is a prime ideal. So J is a prime ideal means what? So now we're recalling statements from abstract algebra. So what is a prime ideal? Prime ideal means that if we have an element P in the ring, for example, and it's a product of two things. If P is an element in this ideal and it's written as a product of two ring elements, so P in J written as AB and AB in the whole ring, then either P is equal to am I correct? Wait. then either A is in J or B is in J. Right? So it looks awfully, if you don't have a feel of what is a prime ideal, is just think of it as a generalization of what's a prime number. So one way to say, we all know the way we think of prime numbers is that yes, exactly two divisors, right? One and itself, positive divisors. So another way to state this is that if we write a prime number as a product of two positive integers, so these two positive integers must be, one of it must be 1, one of it must be p, right? So meaning either p is equal to a or p is equal to b, that kind of thing, right? So this is an analog here. Okay, so this is what a prime ideal is. Okay, and then a maximal ideal, don't need to write much, but that is again very intuitive. Maximal means first thing has to be a proper ideal, meaning it's not equal to the whole ring. And there are no bigger ideals that contain this ideal. Okay, that's a maximal ideal. Okay, so let me see. Yeah, because I want to go quickly to generate examples using this correspondence. Okay, so first example. Yeah. Okay, maybe I should write it down. Okay, so let's say M is a maximal ideal in the ring R. Means that it's a proper ideal that is not contained in another proper ideal. So meaning that if there is another ideal, let's say N, that is sandwiched between M and the whole ring. That's why it means contain, right? So that means, so to translate what I just said in math is that if we have another ideal N that is contained, that is sandwiched between this maximal ideal and the whole ring, then this ideal must either be the whole ring or that maximal ideal. Meaning that there's nothing else sandwiched between them. So that's why we say M is a maximal ideal. So it's like the biggest ideal, it's kind of like one of the biggest ideals in the ring, that kind of thing. So that's what maximum means. Maximum means it's not contained by any other proper ideal. So a maximum, it's the same thing. Maximum subset means it's not contained in a bigger proper subset. Same thing here. Okay. So it's now it's just the special thing is that it has an ideal structure. Okay. So that's a maximal ideal. Okay, so the first example, of course, the way we build this framework, of course, we want AN to be an affine variety, right? If not, why bother spending time building the theory, right? So of course, AN is an affine variety. Why? Because now the easy way is to use this correspondence. We want to show that I of AN is a prime ideal. Right? Because we want to show that AN is irreducible. That's what it means to be an affine variety. It means that it's an irreducible algebraic set. So we already know it's an algebraic set. Just need to show that it's irreducible. So by the theory, instead of going through this definition of irreducibility, we can instead look at the ideal that it corresponds to. If it's a prime ideal, then it's an irreducible set. So that's the elegance of having all these dual correspondence between two areas. Okay, when one side is too difficult, translate to the other side where it's easier, then translate back. Right? So in some sense, this is what a lot of higher math is actually concerned about. Okay, so we want to do the now silent starts kind of argument. So we look at what's the ideal of AN. What's the idea of AN? What is the meaning? What are the polynomials that kill the entire space? The zero polynomial. So it's the ideal generated by. So in fact, it's the zero set, or you can write it in as the ideal generated by the zero polynomial, the zero ideal, right? So is the zero ideal a prime ideal? It's a proper ideal, right? So and then are there any? Okay, maybe you should do it. So okay, so now we claim that this is a prime ideal. Why? What if we write? What happens when we write zero to be a product of two things, where A, B is in our field? A is a field. In fact, an algebraically closed field. So a field is an integral domain, right? Or you don't even need to know if it's an integral domain. You just need to know from linear algebra properties of a field. And this property of field we already know from high school. When two numbers multiply to zero, what happens? Either one must be zero, right? So means that either A is zero or B is zero. In other words, either A is in the zero ideal or B is in the zero ideal, right? So this shows that the zero ideal is a prime ideal. Does that make sense? Maybe I should. And here, actually, wait, no. I should write it as f times g because we're not in. We're actually in the polynomial ring. We're not in the field. But still, polynomial ring, because it's a polynomial ring over a field, so the same thing applies. If you have two polynomials multiplying to the zero polynomial, what happens? Either one has to be the zero polynomial. So, same argument. Okay. So this is the first example. So of course, we want the whole space to be an affine variety. So second case we've done last week. So more like special cases. So if n is equal to 1, then we have A1, right? We call it the affine line over K. So just some terminology. Then again, n equals to 2. So what is a two-dimensional affine space? It's a curve, right? So we call it the affine curve. And then n equals to 3 is a surface, right? Over K. And then when n is greater than 3, it's called a hypersurface, affine hypersurface. And wait, should I do it like that? No, I should write it like that. I should write it like that. We should start with a. Let's talk about n equals to 2 now. So So when n equals to 2, then and consider the principal ideal generated by this polynomial. Be an irreducible polynomial. Okay, so remember, do you recall what it means? What is an irreducible polynomial? Irreducible polynomial is a polynomial that does not split into the product of smaller degrees, right? Right. So we can see the notion of a prime kind of thing here. So from here that this means that the ideal generated by f is a prime ideal. So by the correspondence here, so this prime ideal corresponds to some variety, right? So now you can make more sense of this notation VF. Now that we've introduced the word variety, so VF here is, now I can say that you can read VF here as the variety associated to the polynomial f, or the variety defined by f, the variety, or even the variety of f, that kind of thing. So I hope by now these terminologies start to make sense really. Okay. So it's an affine variety. It's called the, what I said just now actually, what I want to say, it's called the affine curve in A2 defined by f. Remember that? I should say that hold on. Affine line, let's see, affine line. Oh, okay, A1 is an affine line, there's no issue with that actually. But an affine curve, an affine line is more generally, an affine line can be an affine curve. So it's like, just like if we talk about real numbers, we talk about R1 and R2, you can think of like the x-axis is a line, right? And it is itself one dimension. But we can also think of any other straight line as a line. And that is a one-dimensional space in 2D space. Right. You mean here or above? Actually, this I made a mistake here. What I really wanted to present is this actually. Then I talk about different end. So actually, actually this is not right lah. Yeah. Subset is a subset of A2. Yeah. So okay, so this is, so then you can talk about different dimensions. So same argument. Same argument. Let's say f is in the polynomial ring over n variables. And it's irreducible. So again, the principal ideal generated by f is prime. So VF is an affine variety, same thing. So now in this case, VF is called the affine hypersurface in AN defined by f. So you see a lot of these examples presented by Larry next week, right? So more interesting stuff coming up. So for general n, we call hypersurface, right? But for 2 dimensions, we call it a curve. For 3 dimensions, we just call it a surface, right? Then for anything more than 3 dimensions, we call it a hypersurface. So these are the standard examples of varieties that we're interested in. So varieties that are defined by an irreducible polynomial. That is by this argument. By this argument, it's a very straightforward to see that these are varieties. These are irreducible algebraic sets. Yeah. Okay. So you can just attack using this statement. So we want to find what kind of polynomial. And just think of one polynomial. Can think of one polynomial that does not generate a prime ideal. Any good idea? X squared minus y. That's a good idea. That's a good idea, right? So you're doing A2 now. You want to do A2. Oh, minus 1. You mean our first example? Is that this example? Is this irreducible? Yeah, because so yeah, because you can factor x squared minus 1, right? So meaning that okay. Yeah, okay, so let me add a new page. Okay, so our first example, right? A equals minus 1, 1 in A1C, right? So one way to write it is that, so A is actually the union of minus 1 and 1. And these two 1-point sets, they are proper algebraic subsets, right? Because minus 1 is basically V of x plus 1, right? 1 is V of x minus 1. So we have written Z of x squared minus 1, V of x squared minus 1 to be the union of two proper subsets. And these two proper subsets are closed sets because they are algebraic sets. So yeah, that's your example. Is not an affine variety. Yeah, that's a good question. Yeah. Okay. So this is directly, but this method is by directly looking at the topological side of irreducibility. Right? So on the other side, what I do. So meaning, what is the ideal generated by x squared minus 1? We claim that it's not prime. Because we can break down x squared minus 1 into smaller factors. And both smaller factors And then both of these factors are not in the ideal generated by x squared minus 1. Right? Because a prime ideal says that if you have something in this ideal you cannot break down into smaller products of smaller things in the ideal. Right? So meaning that if the ideal generated by x squared minus 1 is a prime ideal, meaning that we've found a factorization, we've written any element, one of the elements, in fact, it means that any element, when you write it down as a product of two things, either one of it must be in the ideal. Right? Remember that. So then if you write an element of a prime ideal as a product of two things, the two things may not be in the ideal. It can be anything from the ring. Then either one of it must be in the ideal. Remember that? Yeah. Yeah. What? I didn't define anything about prime element here. I only define what's a prime ideal. So I get what you mean, but so our language, we have to talk about the ideal. So we didn't have the notion of a prime element here. But it really looks like there's really like a feel, an intuitive and analog with prime numbers, right? So we're just saying that if you break down something in the ideal into a product of two, then either one of that two things must be in the ideal. That's what I mean. Okay. So for example, it's like it's a bit more like if you write a prime number into a product of two numbers, then either one must be a prime. It's more like that kind of idea. You get the difference? Yeah. So this is a definition of a prime ideal, actually. Yeah. Yeah. So we're just using that definition here. So we have managed to write x squared minus 1 into smaller degree polynomials, product of smaller degree polynomials. But neither of this is in this ideal because x plus 1 is not a multiple of x squared minus 1. X, and same for x minus 1, is not a multiple of x squared minus 1. That's why. Okay. Okay, so that's a non-example. And then, okay, I think let's take a break now first, because we have already an hour into the talk. So I just have the maximal ideals. I'll talk about what corresponds to maximal ideals, meaning I want to complete this green picture. Then after that, we'll go to coordinate rings. Oh, okay. Someone mentioned something in the chat. Where is this? Where is this? Someone reflect something. Oh, Xinghao. Oh, okay. Oh, yeah, Xinghao gave a remark on the dimension of a variety thing. So maybe Larry take note of that. Thank you, Xinghao.
Ryan?
Yeah.
Then, I always start the business. With which is very, very easy. From the first thing, I mean, the hardcore practical. I mean, course, business analytics. Yeah. 所以就是那个过程的水平的理论是一个那么它就是看题，它是没有白，有那个有。啊，对，在是那个都在一个，但是你还要解决掉不是在要把时间放多进去，新加坡的话，因为我了解花的觉得为了专业的那么在这边里面全部我在这个车子说好像是有点，这边给你必须要加好，更要上，相对这个整个是有点现在他们在这个另外的。我今天是所有的没有，就真的就是有点难，就是因为现在我懂啊，就一个人一个人的。
Yeah, topology. Algebraic 定义是还有一个理论，那个最重要的那个流。
Zero that's very easy. 发生一个And then, That's the way guys stick like the algebraic is I didn't go
Resume now.
She has like what are the applications of the algebraic but what I find such more to the algebraic not even as a modern ideas. Those what is a classical it's a bit like so that's why tell me why algebraic is study of zero but then it actually the modern
Where is my so what is next? What is next? Then okay, let's continue with one more example. Okay, so next example, I want to do this. What I want to do is what ideals correspond to 1-point sets. Okay, so again, our setting, I won't restate K algebraically closed field, and then let M be a maximal ideal in the polynomial ring in n variables. So we claim that, so the claim here now is that 1-point sets correspond to maximal ideals. Okay, okay, so now, so the argument will go like, so we start with we start with a maximal ideal. Okay, so maximal implies prime. Is it easy to prove? Maximal implies prime because if you take, let's say if you take an element, let's say let's say we take P in M, and P equals AB. Then we claim that A and B must be in A, either A is in M or B is in M. Okay, so I'm stuck. So yeah. So
And generate idea.
yeah.
N and A, let's say. The bigger idea.
Contrapositive. So A in M or B in M. Okay, so suppose otherwise. Meaning we suppose that both A and B are not in M. Then what happens?
And then you can take ideal generated by M and A.
Yeah. So then you consider the ideal generated by M and A. Yeah. Then this is an ideal that contains M. Yeah. And it's not the whole ring. It's not the whole ring. So it's a proper ideal. So we found so by contradiction, it's a proof by contradiction. So we suppose both A and B are not in M. So meaning suppose that this is false. So suppose this is false means both of these are not in M, right? So then we consider the principle, we consider the ideal generated by M, the original ideal, and A. So this is another ideal, that's another AA1 homework. It's okay. So this is another ideal. It's another ideal. And it's obviously not the whole ring. It's clearly not the whole ring. Yeah. What? B is not a. Yeah, I can, yeah. A. If MA is not the.
Yeah, maybe you could.
They can take MD also, and then. Both are not in M. And. Oh, yeah. And then. Okay, maybe if you're a bit more careful, let's just leave it as like that. So we found an ideal that contains M. And so now we're left to show that. So meaning that if we look back at the definition of a maximal ideal, so we start with finding an ideal that is between M and the whole ring, right? We've found N now. So now our N is the principal ideal generated by M and A now. Okay, so that I'm just showing you where the proof is going. So now we want to show that it cannot be M, right? Because A wasn't in M to start with, right? So it cannot be the ideal, the original ideal. So we want to show that it has to be the whole ring. Or if you want to show by contradiction, we actually want to show by contradiction, meaning that so it's not equal to, if it's not equal to M, it must equal the whole ring due to maximality. But due to maximal, but then later we'll show that It's clearly not equal to M, but it's not equal to the whole ring also. So it contradicts maximally. That's the aim of the proof. Okay. So what now? Yeah. Yeah.
So if it is, then 1 is inside here.
Mm.
So we can write 1 as some element of n plus a multiple of a.
Okay, so now we want to suppose towards a contradiction that this is the whole ring. Let me delete this. Okay. So what happens if this is in the whole ring? So the suggestion is that then the polynomial 1 will be in the whole ring, right? And we say the whole ring is generated by these two things. So meaning we can write 1 equals, basically, if you take an elementary number theory, you see a familiar form here. Looks like something, right? Looks like Bazoo's identity, right? So you can write it as something is maybe like something like R, let's say what R X, let's not use X. RU plus SA, right? For some U in M and RS in the whole ring. Yeah.
Are you without an inside here?
Yeah. Okay. So yeah.
Now multiply this equation by d and you will get it already.
Multiply this equation by B. So B is 1 times B, right? So it's B times that whole bunch. So yeah, so this is BRU plus BSA. So now BRU is in M, right? And BSA is AB. What? AB is AB is P, yeah. Okay. So let's write it like that. I want to write it like that. It's clear. So BR times U, and then BS is AB is P. Because we're in a commutative ring, so we can move things around. So AB is P. Remember that P is AB. That's from our initial assumption that we've almost forgot. Right? So meaning what? So U is something in M, right? U is something in M, and P is also something in M, right? So this is a multiple of something in M plus a multiple of something in M. So the whole thing is in M, right? This is in M. This is in M. So the whole thing is in M. So what next? We're done, right? Because we assume at the beginning again, actually towards the contradiction that B is not an M. Remember that? And blah, 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 we show that B is in M. Okay, so that's the contradiction. So contradiction. So that's why this shows that M is a prime ideal. Okay, so so because it's a prime ideal, so again use the correspondence. So we know that VM so so it corresponds to an algebraic set VM. Then what can we say about this algebraic set? Now we have remember we started with a maximal ideal, right? So maximal ideal is, so anything bigger than the maximal ideal is the whole ring. Remember that? So now and remember that this correspondence is inclusion reversing. So as the ideal gets bigger, our algebraic set becomes smaller, right? So how small should it be? So so on the ideal side, anything we go any bigger is the whole ring. So on the affine side, any smaller it will become an empty set. Right? So you have a good guess. 1-point set, right? Because you know 1-point sets are algebraic. So maybe I'm writing a bit informally here. So VM has to be a because of the inclusion reversing property, it has to be sort of a minimal algebraic set in AN. Right? So VM. So the order of VM is 1. Right? Okay. So all good up to here. So VM, what does VM? So VM contains 1 point. That's what it means, right? So in this case, cardinality. It's just cardinality. Explicit form of M. I haven't. Yeah, that's what I want to do later. Yeah. Yeah.
Every set contains a point, right? So
Every 1-point set is algebraic. Yeah, and because we're in an algebraic closed field, so just take the polynomial x minus that point. That kind of argument. Yeah.
are you saying that all
No, I should say that I should say that yeah.
maximal idea corresponds to minimal algebraic sets, and minimal algebraic sets can be of the single points because in every bigger algebraic set you can find a point.
we're actually implicitly using the fact that we already sort of know that 1 point set is an algebraic set. That kind of thing. Because, okay, so now we want to do something. In fact, the next thing I want to do is like, I want to write out what does VM look like. So let's say that VM contains the point A1 through AN. This is 1 point, right? So let's say the point contained in VM is this point. So can we write down a polynomial that has this as 0? Remember, we're in an algebraically closed field. Okay, so meaning that every polynomial has a root. Okay, so now we claim, our claim is that now I want to answer Keesing's question. Now, from here, how do I infer the structure of M? So I claim that M is the ideal generated by everything of the form x1 minus a1, x2 minus a2, through xn minus an. Can you manage to guess this form? Is it easy to at least guess that the ideal should look like that before proving it? Not difficult, right? Because the idea is that let's say just look at every single polynomial of this form. Just look at it one by one. When you plug in this point in, you get 0, right? So when you look at this, the other coordinates doesn't matter. Look at the first coordinate, the other coordinates don't matter. Right? So one direction is easy. Then I didn't do a full proof of this actually. Okay, so maybe let's leave this proof as homework. Should be a set theoretic argument, I guess. Yeah, so mainly what I'm presenting is the fact is that I want to show, the key I want to show is that maximal ideal corresponds to 1 point set. Okay, so now I can complete this picture. So now we know this picture will now look like let me copy this first. Okay. So now we conclude that there are bijective inclusive reversing correspondences. Now we have 3 kinds of correspondence. So the third type we just done from our previous example. So maximal ideals correspond to one-point sets, one-point subsets of AN. That's the purpose that I wanted to mention this example. Okay. Okay. Well, 50 minutes to go. And I haven't even started on the second topic. Okay, so next part are to define what is a coordinate ring. So we start with some people define it for a broader context. Maybe let's do the broader context. So just let A be a subset of A. May not be algebraic. We're mainly concerned when A is algebraic, of course, but just for sake of definition, let's be a bit weaker here. Meaning we be a bit more general here. So you can define the coordinate ring of A. Is the ring that we denote, the standard notation is K A. K is the base field. This K is the base field here. A is the set we care about. So you can talk about the coordinate ring of any affine set. Okay, so the coordinate ring of an affine set is defined to be the polynomial ring in n variables and mod out the ideal of A. Okay, so as the name suggests, this is a ring, and then by just looking at this definition, so when we look at a definition like this, the first thing we want to do is like, how do we feel this statement? How do we feel this definition? So mainly, we want to feel what is the structure of the polynomial rings over K mod out IA. So mod out IA means what? You mod out all the polynomials that QA, right? So what does that mean? So this means that we're kind of like treating all polynomials that vanish at A as the same polynomial, right? So in other words, F in KA may be viewed as functions F from V to K. Okay. H from A, I should say. Right? Because it's a bit like you treat F as a function over the whole space, and you restrict to A. Get a few? So you can see so remember that when we learn functions, we say that two functions are equal if every pre-image corresponds to the same image, right? So this quotient ring can think of it as having the same structure, right? Because we're modding out. So mod IA means we treat everything in IA as the same, right? So meaning we are treating if they're all 0 on A, they are the same, right? So it means we restrict to A. So all of we collect when we collect all of these together, when we treat all of these as the same thing, then as a function it will look like restrict to A. Right? It's the same function. Is this intuitive enough? Make sense? Yeah. So that's why In some textbooks, they give this quotient ring definition. In some books, they'll just tell you it's really the all functions restricted to that set. So I hope you can see why is it an equivalent, sort of an equivalent definition here. And I'm not quite sure why it's called coordinate ring, but I'll mention one idea in a moment. And maybe I can mention something here immediately. So I can say elements of the coordinate ring are also called regular functions. Okay, new definition. Okay, so this is just looking at the definition and try to fill this thing. Okay, so next I want to tell you what structure this set really has. But now I don't care about general case. I only care if it's irreducible. Be an affine variety. Then told you it's a ring, right? As a ring, the coordinate ring as a ring is an integral domain. Then in fact that the coordinate ring is not just a ring, it's also an algebra because you can multiply two functions pointwise. Right? So you can define multiplication. Multiplication is pointwise, right? Multiplication in the coordinate ring should be pointwise, right? You didn't think of it too much. Should be pointwise multiplication, right? So and then you can have the scalars. You can have scalar multiplication also. So it's actually also an algebra as a algebra over K algebra. As an algebra, it's finitely generated. Okay. The proof is very clear. So the proof of part 1 will be using the correspondence just now. So affine variety corresponds to prime ideals, right? So meaning that actually let me write it like that. A is an affine variety if and only if IA is a prime ideal, right? That's from the correspondence. So IA is a prime ideal means what? If and only if. Now this is abstract algebra, meaning that the quotient of the whole ring is an integral domain. So in fact, a one-line proof. So the second fact uses the fact that Ka is a Noetherian algebra. So quotients of Noetherian algebras are Noetherian. And remember, last week, our definition of a Noetherian ring, same for Noetherian algebra, Noetherian module, is that every ideal is finitely generated. Okay. Okay. Okay, so these are the main structures of the coordinate ring. And then another interesting fact about coordinate ring is that let's say we have a finitely generated K algebra. Again, K is algebraic close. I don't repeat that. Algebra. So it's I'm mainly like doing a converse of the previous proposition. It's okay, which is also an integral domain. Then it is isomorphic to some coordinate ring. Okay, so it's kind of like converse of the previous statement. Previous statement says that the coordinate ring of an affine variety is, as a ring, is an integral domain, and as a K algebra, and it's a finitely generated K algebra. So this is like a converse of it. So if we have a finitely generated K algebra, which is also an integral domain as a ring, then it is the coordinate ring of some variety. Okay. So I find this a big result. Proof is not too difficult, but we'll skip it there. So I'll just mention this as a fact. Okay, so that's actually the main properties of coordinate ring that I want to cover. So next is time. Then I've told you what a regular function is. So next I want to tell you. Take just in time. Okay. Yeah. For this proposition, I haven't thought of it actually. But can try to cook up something on the spot. Okay, so calculating the coordinate ring is not difficult, right? So let's say what is the let's see what is the coordinate ring of A1C? A1C is basically C, right, as I said. So by definition, it is what? It is wait. Maybe I should write it as C of KC in my case. So, and then I want our variety is A1. So this is by definition CX. No, I want to do this. What was our example just now? Let's do something here. Forget about it. I can't cook up something on this one. So Okay. So I didn't prepare any examples for this. Okay. Yeah.
You look what algebra is.
Yeah.
You say, oh, here we have algebra K of xy divided
Yeah.
by x minus y squared. And surprise, surprise, it is the coordinate of variety x equal to y squared.
Yeah. That's why okay. So I think that's more or less what we need to cover. Right? And then I skipped the so let's do a checklist. So we started with this, done. These two are the same thing in some sense, same thing. And I skip this. So the concept of Noetherian space is basically the same as Noetherian ring. So it has some chain condition kind of thing. Meaning if you have a chain of Noetherian ring is that when you have a chain of ideals, it terminates at some point. Noetherian space is the same thing. If you have a chain of closed subspace or open subspace, it terminates. Okay, so this part, because of time constraint, I discussed with Larry just now. I'll leave it to him. Okay, so because Noetherian, as Dr. Yan mentioned just now, the concept of Noetherian space is closely related to how to define the dimension of a variety, in particular a fine variety. So that will be dimension of variety hypersurfaces. That's next week, next Thursday. Okay. So and I've come up to regular function. So it's regular function for now. It's just there's another definition of regular function that is a bit more general, but and it's somehow equivalent to the definition that we gave today, but I don't know why. So if we want to discuss next week, maybe we can. And then there's a concept called morphism between variety. So it's like basically it's like because we're doing algebra in some sense. So remember when you in abstract algebra you did group theory, ring theory. The important things were group homomorphisms, ring homomorphisms. Right? So the maps between groups that we care about are the homomorphisms. Same for rings. So the next section will be about what kind of maps between varieties that we care. So we call that morphisms between varieties. Okay, so
This is the coordinates algebra of hyperbola x.
Okay, so okay, so you're saying that M is space of Laurent polynomials. So Z inverse. So is the coordinate ring of the hyperbola xy equals to 1. So and then here so okay, so here we're saying that Z is xy equals to 1. Yeah. So x. Okay. That y map to z inverse, or the other way around up to you. Yeah. 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 So this from abstract algebra is CZ, lit mod out C of xy mod out mod out xy minus 1. Cxy here is the polynomials over C in two variables. Okay, then we have a complex hyperbola xy equals to 1. So we're setting xy minus 1 to be 0. Right? Is it? Yeah. Okay, so I think that's it for today. I'm a bit less prepared for the final part. Sorry about that. So we see next week. We see next week if we want to discuss a bit more on regular function and morphisms, or maybe we can leave it until when we need it. Not sure if Larry will need it. So we have to see next week. Okay, so I think that's all that you will hear from me today. Unless maybe I'll have a cameo next week, depending on what to discuss. Otherwise, that's all you will see from me here. So next week onwards will be someone else. So next week, in particular, next week will be Larry's turn to present. So all the best next week. So, and thank you everyone for attending. Okay, Xinghao has a comment here about coordinate ring because, because I didn't have time to discuss the coordinate functions thing, because that's the next section regular